Welcome to section 4.4. In this section, we're going to be talking about the concept of a spanning set and what it means for a set of vectors to span a vector space. So, to start us off, given vectors v1 through vn and scalars c1 through cn, we say that a linear combination is an expression of the form c1v1 plus c2v2, etc., all the way up through cnvn. So this linear combination, you take all of the vectors given here, you add them, and you scale them up by factors of the constants. So this is a linear combination. If every vector in a vector space V can be written as a linear combination of V1 through Vn, we say that V is spanned by that set of vectors, and we call the set of vectors a spanning set for V. Or alternatively, we say that the set spans V. So, if we have a set of vectors like this, and creating a linear combination of those vectors can create every vector in a vector space, then we say that that set spans the vector space. So, like in other words, if I want to create some vector, say we're talking about R3, for example. If I want to create a vector in R3, the question is, could I create, using the given vectors, could I create any vector I wanted to in that vector space just by using a linear combination of these? If we can, then they span all of the vector space. If there are some missing, where I say, oh, well, I tried to find, this one vector, but I couldn't create that using this set of vectors, well, then maybe it doesn't span the entire vector space. So, for example, talking of R3, let's look at an example with R3. So, is this set of vectors a spanning set for R3? So, what we're trying to figure out here, so we need to determine whether for every vector x, y, z in R3, so if for every vector in R3, if we can create a linear combination of these three vectors to produce this one, whatever it may be. So we need to determine whether for every vector there exist constants C1, C2, C3 such that C1 times 2 negative 1, 4 plus C2 times 3 negative 3, 5 plus C3 times 1, 1, 3 equals x, y, z. All right, so for any vector in R3, we should be able to create it using some combination of these three vectors, if these vectors do in fact form a spanning set for R3. So we're trying to find conclusive evidence that C1 and C2 and C3 will have solutions regardless of what x, y, and z is. So we're not looking for a numerical value for C1, C2, and C3 because that would only work for one specific vector. That would be like if I said, okay, can I create the vector 1, 2, 3 out of these. And in that case, sure, we would try to find specific values of C1, C2, and C3. But we're not trying to do that here. We're trying to show that there will be a solution regardless of what this vector is. So if we set this up as a system of equations, so distribute all the C1, C2, and C3 into everything, and then equate by component, so the X components, the Y components, and the Z components, we get 2C1 plus 3C2 plus C3 equals X. We get negative C1 minus 3C2 plus C3 equals Y. And 4C1 plus 5C2 plus 3C3 equals Z. So this system of equations is equivalent to this equation, and this now can be rewritten in matrix form. So we're going to have 2, 3, 1, and X. We're going to have negative 1, negative 3, 1 with Y, 4, 5, 3 with Z. So you can see here we've got our matrix of coefficients A. We've got it augmented with that solution set V. And each one of these columns is corresponding to one of the constants, C1, C2, and C3. All right, so another way of writing this, like just notationally or symbolically, would be A times C equals V. So again, we're not trying to solve for specific values of C1, C2, and C3 because this is just an arbitrary vector. We're just trying to show that there is a solution to this system. If there is a solution to the system, that means there are values of C1 and C2 and C3 for every vector x, y, z, which means, again, we could create any vector in R3 using these three vectors, or in other words, they do form a spanning set. Okay, so a lot of logical equivalencies here to work through. Now, this matrix in particular, this is a square matrix, a 3 by 3 matrix. So we can talk about that a little bit differently. So we know that if A is invertible, because this is a square matrix, then the C vector with all the C1, C2, and C3 would be equal to A inverse times V. This would mean there is a solution. So alternatively, if we can just show that this square matrix here is invertible, that means that there is a solution for C1, C2, and C3, so this does form a spanning set. Now, we can determine invertibility without actually finding the inverse. We can go ahead and check its determinant. So we know if the determinant of a matrix A is not 0, A is invertible. So in this case, determinant of 2, 3, 1, negative 1, negative 3, 1, and 4, 5, 3. If we compute this determinant, however we like, using any of the methods from chapter 3, we'll see that this determinant actually does give us 0 in this case. So A in this problem is not invertible. So since this matrix is not invertible, that means, so there is no solution for C1, C2, C3. Okay, so this tells us that there are some values of x, y, z where we cannot find values to make this equation work. Okay, so there are some vectors in R3 that do not get covered by the linear combination of these three vectors. Okay, there are some vectors in R3 that cannot be created using only these three, which means, of course, that this set of vectors does not span R3, so it does not form a spanning set. So, thus, our set with 2, -1, 4, 3, -3, 5, and 1, 1, 3 does not span R3. So again, this set of vectors cannot, in linear combination, cannot create every vector in R3, meaning that this set does not span all of R3. Let's take a look at another example. Up here is R2 spanned by these two vectors, 1, 1, and 2, -1. So in other words, can we create any two-dimensional vector using only some combination of these two? Okay, so if we look at the linear combination here, so if we create that first, so that's C1 times 1, 1 plus C2 times 2, -1 equals x1, x2. And the question is, can we find C1 and C2 such that this has a solution for all x1, x2 in R2? And that's the question. Is there a solution, a unique solution for C1 and C2 that we can then apply to find any R2 vector using the linear combination of those two vectors? So if we set up our system of equations, so we've got 1C1 plus 2C2 equals x1, and we've got 1C1 minus C2 equals x2. And we, again, can convert this into a matrix. So we've got 1, 2, 1, -1, augmented with x1 and x2. This is, again, a square matrix, so we don't have to go through the process of row reducing and trying to determine if there's one unique solution. We can just take the determinant here. So determinant of the 1, 2, 1, -1, that's -1 minus 2 is -3, which is not 0. So the determinant of this matrix is not 0, which means that there will be a unique solution for C1 and C2, regardless of the values of x1 and x2. So, regardless of the values of x1 and x2, the system has a unique solution. Thus, R2 is spanned by this set of vectors. So again, what this is telling us is that any vector we can possibly think of in R2, we could create that vector using this linear combination of only 1, 1, and 2, -1. Now, how we would do that, this one didn't ask us to find the values of C1 and C2, but we could. Like, you could row reduce this and solve, get your pivot here, get your pivot here, and then solve for C1 and C2 in terms of x1 and x2, and then figure out for any given point what that combination would be. But of course, the question didn't ask us to do that. But this set does span all of R2. Now, if you look at the examples that we've done so far, you might notice kind of some patterns repeating here in this process. We want to go ahead and formally state some of those. So we have a general principle here. If we have the vectors v1 through vn that are in Rn, then the span of those vectors equals Rn, or in other words, they span Rn. That's another way of writing that. We say they equal Rn if they span Rn. So that set of vectors will span Rn if and only if the determinant of the matrix whose columns are the vectors v1, v2, all the way to vn, if that determinant is non-zero. So the set of vectors spans Rn if and only if the determinant of the matrix created by putting the vectors into the columns of the matrix. That's what this kind of put this augmentation bar here to signify that these aren't components going next to each other. These are columns that are next to each other. So v1 goes in the first column, v2 goes in the second column, etc., etc. Right? And if you look back like at the example we just did, we took 1, 1, and 2, -1, and essentially they got put into the columns of this matrix. We took the determinant of that and got that it was non-zero, and that allowed us to conclude a spanning set. Okay, so this process is technically what we have been using, maybe without realizing that we were using it. But this is kind of the formal statement of this process. So now, as long as we have this situation with a spanning set of vectors here, n vectors in Rn, we can use this determinant as a valid test. Let's take a look at another example. Verify that A1, A2, A3, and A4, these 4 2x2 matrices, span M2 of R. This is the vector space, the set of all 2x2 matrices with real number inputs. So to show that these span M2 of R, we can set up the linear combination. So that's going to be C1A1 plus C2A2 plus C3A3 plus C4A4 equals A. And this would be with A being just a general, like arbitrary 2 by 2, so A, B, C, D. So we have our linear combination. We need to determine if there is a solution for C1, C2, C3, and C4. If we go ahead and compare corresponding elements, so we're going to compare, so the 1 1s will all go together, the 1 2s, the 2 1s, and the 2 2s. Those are all going to go together. So we have C1 times 1 plus C2 times 1 plus C3 times 1 plus C4 times 1 equals A. Then, if we go to the 1, 2 components, C1 is 0, so there's no C1 there. There is a C2, there is a C3, there is a C4. So we get C2 plus C3 plus C4 equals B. That's the 1, 2 component over there. Move on to the 2, 1. We get 0 for C1, 0 for C2, C3, and C4. So we get C3 plus C4 equals C. And for the 2, 2 component, we get a 0, 0, 0. So we get just C4 equals D. Now, the way that this is set up, notice we don't even really need to put this into a matrix and try to solve. Notice this is already in this perfect upper triangular form. Like we've got essentially the pivots right here. We don't even need to go through that process. We can just do even back substitution here to find a solution, right? Because we know C4 is D, C3 is C plus C4 is C. So we could solve that for C3, then solve for C2, then solve for C1. So back substitution gives our matrix A would be equal to C1 ends up being A minus B times A1. C2 ends up being B minus C times A2. C3 ends up becoming C minus D times A3. And C4 was D times A4. So not only can any 2 by 2 matrix A be created with a linear combination of these 4, but we actually found the specific rule to create the linear combination. So, like for example, if we wanted to create the matrix 1, 2, 3, 4, like that, where this is again A, B, C, and D, like that. If we wanted to create this matrix using these 4, we would set it up in this specific way. So we would get 1 minus 2. So we would take -1 times A1. We would take 2 minus 3. So -1 times A2. We would take, that's 3 minus 4. So -1 times A3 plus 4 times A4. If we took this combination of these 4 matrices, it would create this matrix 1, 2, 3, 4. And we could do that for literally any 2 by 2 matrix in existence. And that's kind of the idea, is that we now know that there is a unique solution for any 2 by 2 matrix to be solved as a linear combination of these. So every vector in M2 of R can be written as a linear combination of A1, A2, A3, and A4. Therefore, these matrices do span M2 of R. So these matrices do span all of M2. And in this case, we were able to verify that by actually finding the specific relationship that defines the linear combination. This is what I was talking about in the other example. The other example, we didn't need to find the relationship specifically, but we can if needed be. But in this case, that actually was pretty much the simplest way to do it because back substitution worked really well in this case. So these matrices do form a spanning set for M2 of R. Now, the theorem at the top of the next page, kind of tying back into some stuff we looked at in a previous section, let V1 through Vn be vectors in a vector space V, then the span of those vectors is a subspace of V. So if you have a set of vectors in a vector space, the span of those vectors is a subspace of V. Now, of course, we're hoping, right, if this is V, we're hoping that by taking those vectors, whatever they are, we can create any vector in the whole vector space, right? That would be if the vectors span all of V. But even if they don't span all of V, even if they only cover this portion of vectors within the vector space, this portion will still be a subspace of V. Even if it doesn't cover all of V, it will be a subspace of V. Okay, so the spanning set does create a subspace automatically. All right, let's take a look at an example. If the vector space we're working with is R3, V1 is 1, 0, 1, V2 is 0, 1, 1, determine the subspace of R3 that is spanned by V1 and V2, and does W, 1, 1, negative 1, lie in this subspace? So we're going to take the span of V1 and V2. All right, so the span is going to be the set of all vectors V in R3 such that that vector V, whatever it is, can be written as a linear combination. So C1V1 plus C2V2 with C1 and C2 being real numbers. So again, this is the set of vectors in R3 such that V is a linear combination. Let's go ahead and put the vectors in now. Linear combination of 1, 0, 1 and 0, 1, 1 with C1 and C2 being real numbers. So if we condense this a little bit, so multiply the C1 into all terms, multiply the C2 into all terms, and then combine by adding, we get the general form of the vector V that is in the spanning set of these two has to be C1, C2, C1 plus C2, with C1 and C2 being real numbers. But this is the subspace. So these two vectors, they will span any vector that looks like this. Okay, so any vector that has this form with first component a real number, second component a real number, third component being the sum of the first two components, any vector of that form will be within the subspace formed by these two. Okay, it can be spanned by those two. So now the follow-up question, does this vector lie in this subspace? Well, in order for it to do that, C1 is 1, C2 is 1, the third component should be 1 plus 1, which is 2, but it's not, right? It has a negative 1 in that third component instead. So W, which is 1, 1, negative 1, is not of the form C1, C2, C1 plus C2. So W does not lie in the span of V1 and V2. So those two vectors, they can create any vector of this form. W is not of that form, so it does not lie within the subspace. It does not lie within their spanning set. Right. Let's look at a different kind of example here. What is the span of this set of matrices? So we have three matrices here. The span of those matrices, this is any matrix that can be created using a linear combination of these. So we're going to have a set with C1 times this first one plus C2 times the second one plus C3 times the third one So if we multiply that into the components here, so C1 goes to these two, C2 goes to those two, C3 goes to those two, and add all the results together, the matrix that we get is 0, C1, C2, negative C1, 0, C3, negative C2, negative C3, and 0. This general form of matrix might look familiar. So the idea of zeros on the main diagonal and then terms up here and their exact opposites down here. This is a skew symmetric matrix. Okay, not symmetric, but skew symmetric. And this is the set of all 3 by 3 skew symmetric matrices. So this is the set of all 3 by 3 skew symmetric matrices. That is the span of these 3 matrices. So in other words, if you take these 3 matrices and create a linear combination of them, you can create any and all 3 by 3 skew symmetric matrices using a linear combination of these 3. Okay, so they span all 3x3 skew symmetric matrices. What about this example down here? What is the span of the set 1x, x squared, and x cubed? Well, if we create our linear combination, so that's c1 times 1 plus c2x plus c3x squared plus c4x cubed. Well, this just looks like a polynomial, right? This is the general form of a cubic polynomial. Now, it is possible that one of these values of c could be 0. Any of them could. So it's not necessarily a polynomial of degree 3. It's a polynomial of degree 3 or less, because if this one's like 0, then it's a polynomial of degree 2, etc., etc. So this would be all polynomials of degree less than or equal to 3. And we do have a vector space for that, right? This is P3 of R. So P3 of R, that is the vector space, the set of all polynomials of degree 3 or less. Okay? So in other words, you can create any polynomial of degree 3 or less using a linear combination of these 4 terms. Right, which hopefully makes sense, because like if you had the polynomial, any polynomial you want, you could just make the numbers c1, c2, c3, and c4 what you want to create that polynomial. All right. Taking a look at the next example here. Find a spanning set for the null space of this matrix. So remember, the null space is going to be the solution to this homogeneous system of equations. So that x vector, that x, y, z, that solution set is the null space. Okay, so if we can find the solution set, we can then find a spanning set for it. Okay, so let's set this up. 1, 2, 3, 3, 4, 5, 5, 6, 7, augmented with all zeros. If we do the row reductions here, which I'll go ahead and spare us that calculation, but we should get 1, 2, 3 with 0, 0, 1, 2 with 0, and then an all 0 row at the bottom. Okay, or some equivalent form of this. Again, the exact operations you perform are not necessarily unique. You could get some alternate but equivalent version of this, but it should be something like this. So this would be our row echelon form. This gives us Z is that unpivoted column. So that's going to be our free variable. Y plus 2t is 0, so y is negative 2t. And x, that's 2 times negative 2t, so that's negative 4t, plus 3t is negative t, so add that over. X is also t. So the null space of A, of this matrix, this is the solution set. So the set is t, negative 2t, and t, such that t is a real number. Now, this isn't what it asked us for. This is the null space. So this is the solution to this system. But it wants the spanning set for the null space. So for the spanning set, we need to create a linear combination. So if we set this up as a linear combination, we can go ahead and factor out the t. So t times 1, negative 2, 1 equals x, y, z. Right? Any solution to this system has to have this form. But this is a linear combination, right, of this vector with t acting as that constant, right, acting as like C1 in this case. So the spanning set is just the set of this one vector, 1, negative 2, 1. So this tells us that if you want an element of the null space for this particular matrix, you need a linear combination of this vector to get there. And that's, again, what we have right here, a linear combination of this vector. There is no like sum piece. It's not, plus something, but it's not needed because there's only one vector here. So again, the spanning set is just this one vector. Any multiple of this vector will produce an element of the null space. Okay, so the null space has infinitely many solutions, and all of them are going to be multiples of this one vector. Okay, they're all linear combinations of that one vector. So that vector is our spanning set. Now for the next one, find a spanning set for 3x3 symmetric matrices. So we already saw an example where we constructed, given the spanning set, we constructed those 3x3 skew symmetric matrices on the last page. Here we're kind of going backwards with this. So a spanning set for 3x3 symmetric. So if we go ahead and create an arbitrary 3x3 symmetric matrix, so we're going to have A, B, C, and if this is B, then that has to be B, and that has to be C. D, E, and if that's E, then that has to be E, and then F. This is the general form of a 3x3 symmetric matrix, right? Opposites across the main diagonal are all the same. Let's break out these variables, or typically we refer to it as like busting out the variables. So we're going to have the A, and there's one here and none anywhere else. B is going to be here and here. C is here and there. D, oops, just one in the middle there. I think I need to shrink this down a little bit. Plus E. And F, our last one. All right, so in this case, we have our general 3x3 symmetric matrix here. And again, this is what we call, so bust out the variables. So we break this into a linear combination, kind of like we did up here, except there was only one term. But we bust out the variables, so use those variables as the coefficients in the linear combination. And in doing so, the spanning set, the vectors, right, that list of vectors that form the spanning set, that is everything else. That is those 6 right there. Okay, so our spanning set that would be 1 0 0 0 0 0 0 0 0, and etc. etc. I won't write every single one of these down again, but you get the idea. So the spanning set is all of these vectors. If you created a linear combination of these vectors, like we have right here, you could then create any 3x3 symmetric matrix. Okay, so it's the same idea that we had in the skew symmetric example on the last page, but we're going the opposite direction now. Here we created the general form and busted out the variables to create the linear combination, and then created the spanning set from there by just listing the vectors themselves. All right. Then taking a look at this next example down here, is this set of vectors a spanning set for P3 of R? So to make this determination, we would create a linear combination of all of these and see if we can use that linear combination to create any polynomial of degree 3 or less. So we get C1 plus C2 times 2 plus 3x. This was C1 times 1. Plus C3 times 4 plus 5x plus 6x squared plus C4 times 7 plus 8x plus 9x squared plus x cubed equals a plus bx plus cx squared plus dx cubed. So that arbitrary polynomial of degree 3 or less. Now, what we can do to set up our system of equations is we can rearrange this not by individual vector, but by the power on the x's. So we can lump all of the constants together. We can lump all of the x's together, all of the x squareds together, and then the x cubed. So if we regroup this, the constant terms that we have a C1, a 2C2, a 4C3, and a 7C4, plus, for the x terms, we have 3C2 plus 5C3 plus 8C4 times x. Plus for the x squareds, we have 6C3 plus 9C4 times x squared plus just a C4 on the x cubed. And that equals the same thing. Equals the same thing. This gives us the system of equations because now this constant component here has to be equal to this one. The coefficient on the x over here has to be the same as the coefficient on x over here. And the coefficient on x squared has to be the same, and the coefficient on x cubed has to be the same. Oops, that should be x cubed. So we get C1 plus 2C2 plus 4C3 plus 7C4 is A. 3C2 plus 5C3 plus 8C4 is B. 6C3 plus 9C4 is C. And C4 is D. We saw a previous example kind of like this where we did back substitution. It's not asking us to find the actual linear combination. We're just trying to show that there is one. So if we put this into the matrix form, so that's 1, 2, 4, 7 with A, 0, 3, 5, 8 with B, 0, 0, 6, 9 with C, 0, 0, 0, 1 with D. Notice this is an upper triangular matrix. We have all of our proper spots here for our pivots. This is going to have one unique solution. You can also look at it using the determinant. So notice the determinant of this matrix is not 0. In fact, it's actually 18. But this tells us there is a unique solution for C1, C2, C3, and C4. Okay, so that means for any vector, a plus bx plus cx squared plus dx cubed, for any 3-dimension or less vector or polynomial, there will be values for C1 through C4 that give us a solution. Okay? So in other words, we can create any polynomial like this using C1, C2, C3, and C4, using this linear combination of these 4 vectors. So, therefore, the set does span P3 of R. So this set of vectors here does span P3, so it is a spanning set for P3. Now, one final thing to note here that the question is, this set of vectors does span all of P3, so we can create any vector in P3 using this set of vectors. The question is it only this set of vectors that can create all of P3? And no, that is not necessarily the case. There are plenty of sets of vectors that could span all of P3. So we need to make a note here that spanning sets are not unique. So this is why we phrase it, is this a spanning set for P3, not the spanning set for P3. There are infinitely many different sets of vectors that can span this vector space P3. This is just one of them. Okay, and we'll talk more in upcoming sections about how we can span vector spaces like this more efficiently. What are some of the better choices to use for spanning sets for vector spaces? But these spanning sets are not unique. Okay? There are many different spanning sets for any given vector space. But to answer the question of this example, this set of vectors does span all of P3 because we can create a linear combination with a unique solution for C1 through C4. And that brings us to the end of section 4.4, and that is the beginning of our conversation on spanning sets. We will see these coming up later in the chapter as well, and we'll see again how we can kind of combine them with other vector space ideas to answer more questions and span more types of vector spaces and do it even more effectively and efficiently. So we will talk about all of that in the coming sections.